Hey, welcome back to Computer Science Theory. This is comms W3261, offered Summer B 2021 at Columbia University. And this is Lecture 10, Making Hard Decisions, where we're talking about decidable and undecidable languages. And this is part 1 of 2, if you're on YouTube. So our teaser question for the day. So last time we began talking about proving that languages are decidable. That means showing that there is a Turing machine that always accepts on a string in the language and always rejects on a string that's not in the language. So a decider, a Turing machine that never infinitely loops. And our teaser question is the language a DFA equals an encoding of BW such that B is a DFA that accepts W, so W is a string, decidable. And for this, we'll think high level. So we also talked last week about different levels at which we could describe a Turing machine. So of course, we always have our formal level. Our Turing machine is at bottom, a box of math. It's a 7 tuple. But eventually, well, very quickly, we got tired of the box of math model because we wanted to design bigger and more powerful machines. So we moved up to an implementation level description, where we talked about how the head moves around, how the head makes its decision, and how the Turing machine manages the memory stored on the tape to make sure it always has the information it needs available to it. Then we got tired of implementation level descriptions. We started to suspect, along with Church and Turing, that Turing machines could do almost anything a regular algorithm could do, almost anything that a program could do. So we moved up once more to high-level descriptions, where we no longer care about the details of what is on the tape or the head. We just treat our Turing machine as something which is able to generally manipulate finite information in finite ways. So if we can imagine writing it down, if we can imagine checking it, if we can imagine manipulating some data structure in a program, we can imagine doing it with a Turing machine. So that is the frame with which we're approaching this teaser. And to go over this teaser, we're looking at a language of encodings. So the input, as always, is a string, but the string is an encoded Turing machine and an encoded string. And we'll accept that encoded string if it encodes a Turing machine and a string such that the Turing machine accepts on the string. So B will accept on W. So if you want to take a stab at this teaser, it's more of a conceptual teaser. Pause the video now. I'll come back in 2 seconds and explain how we can think about this. All right. So let's see. First thing to recall is that decidable means the TM always accepts on strings in the language. And it always rejects on strings not in the language. So our job here is just to write down a high-level description of a Turing machine that does precisely this, that decides this language ADFA. So M1 will look like the following. On input, B, W, we always have our kind of implicitly assumed step 0, which is reject if the input
is not an encoded DFA followed by a string. So of course, we want to reject bad input because that's just not relevant to the problem we're trying to solve. And then all we have to do is simulate B on W and accept or reject if B accepts or rejects. So simulating a DFA is an easy thing to do at the high level. A DFA is a finite automaton. So we can certainly write it all down. We're not going to run into infinities there. And we just follow the transition function to figure out how B works on W. We're also guaranteed to decide, that is, always accept or always reject, because DFAs never run into infinite loops. They take one step for each character in the input, and after the input is exhausted, they stop. So our TM can't possibly run forever, and that's why M1 is a decider for this problem. And of course, now that we have a DFA, there's no reason we can't say, all right, what about A sub NFA, where this is equal to the encoded BW such that B is an NFA and B accepts on W. So this is also decidable. We won't write down the formal two-step Turing machine, but it's very similar to M1. So one way would be simulate all branches of computation. In parallel. One reason we're simulating in parallel, like it would be hard to come up with a Turing machine that would run into an infinite loop on an NFA, but not impossible. Maybe you have one branch of the NFA that goes around an epsilon loop forever. And if we just do a depth first search of the tree of all NFA computations, we might end up in an infinite loop simulating that branch. So for that reason, it'll be important when we're simulating an NFA to simulate all the branches in parallel. But another thing we can do is we can just convert B to a DFA. So we know how to do that. We just make a set of states equal to the power set of the states in an NFA. So we just convert B to a DFA, and then we use our original decider, our machine M1, to run our new DFA on W and accept if and only if the DFA accepts. And we can ask these questions for other ways we have of describing languages. That is, we can treat our mathematical object as an encoding, and we can say, does this thing describe, recognize, generate a particular string? So, you can imagine this language A sub regular expression, which takes in an encoded regular expression and a string W and accepts if and only if R is a regular expression that generates W. This is also decidable. So one way you could do this is you could design a clever machine to break down the regular expression and evaluate it on W and try a bunch of different ways of creating strings from R. Or
you could do the classic computer scientist thing. This is one way in which this course is like other computer science classes in that we're very lazy and we like to reuse code. We know we can recognize DFAs. We now know we can recognize NFAs. So we'll just use our previous procedure. We'll say, hey, Turing machine, turn this regular expression into an NFA, then turn that NFA into a DFA, and then reuse the program we sketched out above. So we don't have to do any additional work to see how to decide this language. So, when in doubt, be lazy, as long as being lazy works. So that's our teaser. And we've seen a couple more ideas of how you can use Turing machines as deciders and describe Turing machines at a high level. Announcements for today. Homework 5 is due today. That is 8/2/21 at 11:59 p.m. Eastern. And then homework number 6, which, because it's due the same week as the final, will be a short homework. That'll just cover, for the most part, what we're doing today. It will be due the day before the final, and I recommend doing it because one of the problems on it helps you study for the final. That is due 8/9/21 next Monday at 11:59 p.m. EST. But again, it's short. There's extra credit on it, so it's worth doing as part of your final study. The final itself is on 8/10 through 8/11. You can take it during a 12-hour block of your choice. See the ed post for more information, or come into office hours with any questions about studying or preparing or how it's going to be run. I'm also going to be offering a review session, well, 2 review sessions. One in person from 1 to 4 p.m. on Monday in the CS Lounge, and another one virtually the same evening. That is 5 to 8 p.m. Eastern on Zoom. So come by then. It'll be a combination review session and regular office hours. We'll see how many people we have, but we'll most likely be talking through homework problems and final prep, and we'll have a sketch of review topics for the final before that point. Final announcement is I'll be bringing in either donuts or bagels, depending on a vote of the in-class today on Monday. So there will be either donuts or bagels and coffee on Wednesday. If you're in the city and you can't attend this class, I'd highly encourage it. Don't worry, I will not hold it against you if you've been attending virtual classes so far. I understand that's way more convenient for many people for a variety of reasons. But if you can make it, we'd love to see you. We'll hang out. Hopefully we'll be able to wrap up about half an hour early and have a chat about the course. So please do come for that if snacks motivate you. I would love to see more faces. That's announcements for today. The readings that correspond to this lecture are Sipser 4.1 on decidable languages, and Sipser 4.2 and 5.1 on undecidable languages. So, sketch of what we're going to do today is we are going to review last week. So we'll talk about variant Turing machines. We'll talk about the Church-Turing thesis. We'll talk about descriptions of Turing machines at different levels. We will show some more decidable languages. So we'll get really familiar with these proofs of decidability. And then
In the third part, we will talk about some undecidable languages. So to prove that languages are not decidable, we'll have the pumping lemma for Turing machines, in which you divide strings into 19 parts, and you have to rule out a variety of cases and subcases. No, there's no more pumping lemmas. Forget that. We're going to do much, much cooler proofs that descend from contradictions using paradoxes. There's no pumping lemma for Turing machines. So that'll actually be pretty fun, I think. You'll get to see this brain-melting proof that deciding whether a Turing machine halts or deciding whether a Turing machine accepts a string is undecidable. And you can fully expect it to be brain-melting. Like, this is brain-melting for very experienced people, and we'll just have fun with it. That's what's coming up in the second part of this lecture. All right. So, review of what we did last week. We saw 3 variant Turing machines, and we observed various theorems that related them back to ordinary Turing machines. So in particular, we saw multi-tape Turing machines. So with a little picture, we had our regular input tape with the input on it. And then we also had some number of other blank tapes that we could use as we chose. We moved all the heads at the same time, but we maintained one state in the state control. So the transition function looked like, give me a state and tell me K tape symbols, that is K symbols read by the K heads. And if you give me those things, I'll tell you which state to move to. That's one state for the whole machine. Which K symbols to write down on my K tapes, and also how to move my K heads. So we said we'll add a stay put operation, although that really doesn't generalize much, and we'll specify K movements for the K tape heads. And we showed by simulation that every multi-tape Turing machine has an equivalent single tape Turing machine. So if you ever want to prove that a Turing machine can decide something, you're welcome to assume multiple tapes, because of course you can just use the reduction to simulate that machine you've just created. Likewise, we never get far without introducing non-determinism. So we said, well, what happens if we add this superpower of non-determinism to Turing machines? As usual, we get a transition function that goes from one state and one tape alphabet symbol to a set of states. So we use our power set notation to talk about the subset of all the possible places we could transition to and all the things we could do. So it'll be a subset of triples, a subset of new configurations consisting of a state, a thing we write on the tape, and a place we move. We had also another handy theorem that told us every non-deterministic Turing machine has an equivalent deterministic Turing machine. I'm using N and D to stand for non-deterministic and deterministic respectively in this abbreviated theorem. So again, like multi-tape TMs, you want to assume non-determinism to prove decidability. You are welcome to. We showed how to simulate that. Simulate the non-deterministic branches, do a breadth-first search of the computational tree. And then we also considered another modification of the Turing machine called an enumerator, which is not quite, I mean, it is giving the Turing machine an additional power, but it doesn't enhance the Turing machine's computation. Instead, We imagine that we have hooked up our Turing machine to a printer. It doesn't get to edit anything that it's written down, but it can write down, it can copy its tape to this printer. You can imagine this printer is printing out one line with the tape contents whenever we want it to. So these are Turing machines with an additional print function that doesn't affect computation. They enumerate, which in our case, enumerate just means write down on the printer, some possibly infinite language over the course of computation. And we showed a theorem that doesn't quite show equivalence, but it certainly shows a close relationship between enumerators and Turing machines. We said that a language is Turing recognizable. And if we recall what recognizable means, that's just, it's a weaker condition than Turing-decidable. So a language is Turing recognizable if a Turing machine exists that can halt and accept on every string in the language. And it doesn't accept strings not in the language, but what it does on those strings is not defined. So it could loop indefinitely on some string that's not in the language. So a language is Turing recognizable. We also showed a language is Turing recognizable if and only if some Turing machine, sorry, that's a Turing machine, some enumerator enumerates it. We talked about levels of description. So in particular, we sketched out 3 levels at which you could describe a Turing machine. We want precision at every level, but every time we go up a level, we're willing to sacrifice some detail and assume some knowledge of how we could go from this higher level description to a lower level description that specifies more of the Turing machine's behavior. So in particular, a formal description is just a 7-tuple. So that's when I write down what the states are, what the alphabets are, and precisely how my transition function works. Above that is an implementation level description. Where this is a prose description. Prose, hopefully we have some English majors in the room. It doesn't mean you do formal descriptions in poetry. In this case, it just means you write sentences instead of writing math. It's a prose description of tape management. That is, you say how things are encoded on the tape and how you manipulate information on the tape to make sure you always have the information you need to refer to. And head movement. So you don't have to actually write down the transition function, but you do have to say, when we see this, the head turns around, or the head shuttles back and forth between these 2 strings written on the tape. Above the implementation level description is the high level description, which for the most part is all of the Turing machines we will describe today will be described at the high level. And this is a precise prose description of an algorithm, ignoring implementation details. So we can think of this as manipulating finite or finitely representable math objects. So if I'm doing a high-level description of a Turing machine that operates on a graph or that simulates some other Turing machine or some other automaton, I don't have to worry about how I'm actually writing that down and encoding it on the tape. I can just pretend my Turing machine has access to this object and can freely manipulate it as long as I'm not doing, for the most part, anything infinite or anything that requires information that I don't have. As long as the information is finite or I can reasonably be expected to write it down on the tape, then I can use it later, however I want. And this movement from the formal description to the implementation level description to the high level description, this exploration of all the things Turing machines could do led historically to this philosophical thesis. So I suppose you could say this is a law like gravity is a law. This is a law about what we've observed about computation and what we think about the world. Actually, don't quote me that it's a law like gravity is a law. Physicists will object. This is not the same thing. But the Church-Turing thesis essentially says that our intuitive notion of an algorithm or a completely specified process corresponds exactly to what a Turing machine can do. So this is what leads us to say things like, this function is computationally hard, or this function is not computable or not decidable. Implicitly, what we mean by all of these things is we mean computationally hard, not computable, not decidable for a Turing machine. But the Church-Turing thesis licenses us to say, well, that's just a fact about computation in general, because Turing machines capture this huge abstraction that, as we saw last time, is also captured by a bunch of other equivalent models. So it's not specific to this idea of a state control and a tape. You can capture it with tiles. You can capture it with different machines. You can capture it in Minecraft. You can discover this hard core of computation in many different ways. We just choose to tap into this eternal notion with our particular abstraction, the Turing machine. And we use this equivalence to talk about computation really, really generally. So that's what we did last week. So we've seen several decidable languages already. We're going to do a couple more. And one benefit of this is just we'll see more about how to think creatively about proving decidability. Now we're kind of moving on from focusing on the concept of decidability itself. This idea, a language is decidable if a Turing machine will always stop and either accept or reject. And moving on to thinking about ways of proving decidability, and also thinking more about the languages themselves. What does their decidability say about these languages? So we'll be thinking about the languages as the interesting thing as much as the automata. And previously, we've dealt with some pretty trivial languages. These are languages that often have meaning, have some conceptual power. So here's an example. And the example is the language eDFA, which I'm going to define to be a description of A, such that A is a DFA, and the language of A is the empty set, the set of no strings, the empty language, decidable. So in other words, we're going to get some encoding of a DFA. At a high level, we can think of just having this DFA, and we have to determine, does this DFA recognize the language of the empty language? Or equivalently, does this DFA accept never on no strings? Of course, recall that the empty language, which is an empty set, is not the same as the language containing the empty string, which is a language that has a member, just has the empty string. And the answer is yes. You can see this by writing down a Turing machine that decides this language. We'll say T on some input string. Our step 0 is, of course, reject if the input string does not encode some DFA. So that throws out all the garbage and makes sure we're dealing with some coherent input. And then what we'll do is we will just sort of look at all the states that are reachable within our DFA. So we'll say, okay, mark the start state of A, and then mark all states accessible by one hop of the transition function on some input from A. And then 3 is we'll just repeat step 2 until we can't find more accessible states. And repeating 2 does create a loop, but it's always a finite loop because the number of states is finite, the number of state transitions is finite, the alphabet is finite. So eventually, we're certain to get to a point where there are no new states that are accessible from marked states. And 4, except if and only if we have marked no except states. Reject otherwise. And why this works? Well, this follows from a fact about DFAs. So any transition in a DFA is a transition we can take at some point, right? Every transition in a DFA is marked with some string in the language. If we find a sequence of transitions that takes us from one state to another state, there's got to be some string that takes us there. So essentially, we just say, we're going to do a big search of all the states, find all the accessible states. If an accept state is accessible, that corresponds to some string in the language. And this DFA is not in the language eDFA. If we can't find any accessible accept states, well, then there's no strings that make this DFA accept. So this DFA is in the language eDFA. Close my quotation marks there. Oh boy, I just realized that I write all of these big quotation marks and parentheses and things like that in the notes. I'm sure somewhere in the notes is an open parentheses without a closing parenthesis, and I'm sure it's driving some people crazy. So I'm not going to go back and fix it, but I do apologize. So again, we know this always terminates because our DFAs are finite. Let's do another one. So we'll define the language EQDFA to be the language of pairs of encoded DFAs. So EQDFA is inputs A, B, such that A and B are DFAs. And the language of A equals the language of B. The question is this decidable? So how might we decide this? The first idea that might come to mind is try all the strings, reject if they behave differently. And this will indeed eventually reject any pair of candidates that don't work, but it's not a good way to get a decider because of the possibility, well, what if A and B do recognize the same language? There's an infinite number of strings we can try, so we're going to loop forever. We're never going to accept. So we have to be a little more clever. I'll show you a clever way to do this. This is not necessarily a way you'd come up with immediately. But I will star this in case, I'll star this in case you're doing the final and you're desperately trying to solve some problem. And you look back at your notes and you see this start idea and you realize, oh, hey, I can prove a language is decidable by using closure tricks. So if that's you, welcome back. I'm glad you found this. I hope it helps with the final. Clever idea 2 is we know some facts about regular languages. So here are some facts. Given DFAs for A and B, we can construct DFAs for the following languages. So we can construct DFAs for A union B. So we showed a construction that does that directly. We can also just use closure under union and go through NFAs if we wanted to and convert back to DFAs. But we saw this essentially. Our proof was we simulated both and accept if either accepts. We could also do a intersection B by a similar simulation proof. We simulate both our DFAs and we accept if and only if both accept. And finally, at one point, we showed that DFAs were closed under complements. So this is achieved by swapping accept and reject states. So a DFA accepts if and only if the single computational path through it reaches an accept state. So if we switch all the accept and reject states, we get a DFA that recognizes the complement language. That is all the strings over the input alphabet that are not in the language. So we can construct these things, which means if we're doing a high-level Turing machine, our Turing machine can construct these things given DFAs. So thus, given DFAs for A and B, we can build a DFA D such that the language of D is equal to the language of A intersection complement of language of B union language of A complement intersection with language of B. So what the heck did I just write down? Well, this is strings in A, not in B, or I should say the language of A and B, but that's And this is in the language of B, not in A. And we want anything which is, so the language of D will be all the strings that are recognized by A and not by B, and recognized by B, but not by A. So if we drew a Venn diagram, we're just capturing this portion. The reason this is convenient is that this language is equal to the empty set if and only if the language A is equal to the language of B. Because what does it mean if A and B are the same language? Well, it means there's nothing in A that's not in B, nothing in B that's not in A. Similarly, if we got two languages and they don't have any elements that are in one but not the other, they're the same language, the same set. So we've changed our problem into the problem of detecting whether this language is the empty set, and now we get to be lazy. Now we can use our decider for EDFA on the language of D. So in other words, we can test whether or not this new amalgam language is empty or not, and that's the same as testing whether or not A and B are equivalent. So in other words, to decide EQDFA, define the following Turing machine. F says, it's very ugly. F says on input A and B, where A and B are DFAs. So from now on, I may just write this. And implicitly what this is saying is check and make sure A and B are DFAs, reject if they're not. This is taking the place of step 0. It's shorthand. So on input to DFAs, we construct D as described. So D is a DFA that recognizes this language up above. LA intersection not LB, or not LA intersection LB. Then we run a TM. So run means simulate here. That decides E DFA on D. So in other words, we've already shown that EDFA, the language of all DFAs that don't accept any strings, is decidable. So we can assume that TM exists and we can simulate it on our new Turing machine. And finally, we accept reject if our simulation accepts or rejects. Excellent. So we've done something cool here. We reduced a problem to another problem. We'll talk about reduction formally later. We said, how do we decide this language? Well, give me two DFAs. I claim I can build a new DFA that recognizes the empty language if and only if my original two DFAs were in the language I'm trying to recognize, and then I can reuse some old code to simplify my job. So I'm also going to write down a few bonus facts. So we don't have time to prove all of these things, but they have interesting proofs. They're in Sipser, section 4.1. So you can look them up if you want. Obviously, since we're not proving them in lecture, you won't be responsible for the proofs, but I will write down these things as facts that you're allowed to cite. So fact 1 says that ACFG, this is like ADFA, but for context-free grammars, so this is input G and W such that G is a context-free grammar that generates the string W is decidable. Fact 2, ECFG, that is, give me a context-free grammar and I'll tell you whether or not it generates the empty language, is decidable. And fact 3, the third analogous fact, EQCFG, that is, give me 2 grammars, G and H. I'll tell you whether or not they're equivalent. This is also decidable. So you have to be relatively clever when putting these things together to avoid infinite loops. It's hard to try all the derivations of a string because some derivations might include an infinite number of steps, but Chomsky normal form, which turns out to limit the number of steps it takes to derive any string, will help us out in these proofs. We can use this. So if we assume that we have these solid facts, we can use them to prove something long overdue about the decidable languages, which is that they are a bigger class of languages than we've seen so far. I've probably referenced that already, but now we can make it formal. So the theorem is that every context-free language, that is, language described by a context-free grammar, is decidable. Some Turing machine exists that decides this language. The proof idea, we showed previously that every context-free language is recognized by some push-down automaton. So to show that they're all decidable, we just need to show how to simulate a push-down automaton with a Turing machine. So the proof idea is we will show how to convert a PDA into an equivalent Turing machine. We'll just write out the proof. It's a few lines assuming these facts that we have not proved, but I'm telling you are true. So let's let G be a context-free grammar for some language A. And we'll let S be a Turing machine that decides the language A sub CFG. So in other words, we're assuming we have some Turing machine that tells us, given a grammar and a string, whether or not we can generate that string using that grammar. We'll define the Turing machine, M sub G, as follows. So I'm trying to leave this fact 1 on the screen so you can refer back to it. M sub G on input W. We just run S on G, W. And this is okay because G is finite. By definition, it's a context-free grammar. And we'll just assume G is hard-coded into MG. So what this means is we have some set of states that either tells us how to write down a description of G or explains to us how to run G. This is something that we can assume if we're doing a high-level description. So we can just run our Turing machine for AC of G on GW, and then we're done. We accept or reject if S accepts or rejects. I'm sorry, I think I've given you a mistake has crept into my notes. We're just going to cross this out in red because that's not the proof idea for this proof. I just wrote it down without thinking carefully about what I was doing. I gave you the wrong proof idea. Hopefully that's not too confusing. We are proving that every context-free language is decidable. This proof has nothing to do with push-down automata. I think it's probably, that was an old note from an earlier draft of this lecture where I considered proving these facts above. So ignore that. We did prove that every context-free language is decidable, however. We said, give me some context-free grammar, and here is a Turing machine that decides whether any input can be generated by that grammar. The Turing machine is simple. It just relies on this stated fact that we can recognize a pair of a grammar and a string and figure out if that grammar generates that string. Cool. This, of course, like every time we show inclusion of language classes, updates our picture of the universe. So our new picture of the universe, well, we have our itty bitty baby class of finite languages. Hanging out inside our class of regular languages. That is languages recognized by DFAs, recognized by NFAs, generated by regular expressions. This is hanging out inside the bigger bubble of context-free languages, which are those generated by CFGs or those recognized by push-down automata, which is hanging out inside our bigger bubble of Turing-decidable languages. So this is what we just proved, is that all the context-free languages were inside the decidable languages. And based on our definition of decidability and recognizability, we know that every decidable language is recognizable by definition. And we will see some languages that are recognizable, but provably not decidable. So we actually have one bigger final class, that is the Turing recognizable languages, which we also saw are equivalent to these languages we called recursively enumerable, because there were enumerators that could write down everything in them, even if that writing down process was an infinite process. So this is a much richer universe. I do wish we had some overlapping circles, but in some ways, a universe without overlapping circles is neat and clean and beautiful. If I were to say, you know, which is more complex, this language that's regular or this language that's Turing decidable but not context free, you would have a decent answer to that. You'd be able to tell me, well, okay, my regular language is in this little bubble. My language that's Turing decidable but not context free is in this big bubble. And you'd have a relatively good leg to stand on if you wanted to convince me that second language was more complicated, because you'd be able to say, well, little simple computational machines recognize the first one, but you need a big, powerful one to recognize the second one. So, it's probably too grandiose to say we're learning about concepts, learning about the universe, but this picture's cool. Showed that hopefully we've learned a few things in this class. That will do it for part 1 of this lecture. So next, we will go on to this Here There Be Dragons region, far outside the bounds of our largest egg. We will talk about countable and uncountable sets as a way of getting us into undecidable and unrecognizable languages.
So thank you very much for watching. I'll see you in the next video. Bye for now.